No, this was not running the whole time, thankfully. I'm sure I said something that I shouldn't have. I know, right? All right. So, in Chapter 6, we're going to be looking at angle sum difference and multiple angle identities. So, what we're going to do is we're going to figure out how to do like sine of like angle 1 plus angle 2, or angle 1 minus angle 2, or 3 times angle 1, or something like that. So we're going to start by talking about the sum and differences. So what we're going to do right now is, stop talking please, is I'm going to derive some of these angle sum and difference identities. This is not something that I expect for you guys to be able to recreate for me. So I don't, like, if you just want to kind of sit and watch. Was that the whole class? Oh, okay. It's like,
we're done. That was just the.
I mean,
what if all you want to do is kind of sit and watch and like try to understand and not worry about writing this down? That's fine. Okay, so this is this proof or derivate. It's really a derivation. Like I'm showing you where this formula is going to come from. And it's a little bit kind of constructive, like we have to draw some pictures here. And it gets a little bit messy. But if you just want to kind of follow along and kind of watch what I'm doing, I think that's appropriate. I don't know that you really would need to reproduce this for me. Okay? So what we're going to talk about here is angle sum and difference formula. So let's say we have two angles. I'm going to call this one V. I'm going to call this one U. And I'm going to call this one theta. Everybody okay with that? So, looking at this picture, how can I relate U, V, and theta together? Is there an equation I can write that relates the three of these angles together? Theta plus V equals U. Okay, I'm going to write it. That's true. I'm going to rearrange that, though. And I'm going to write it as theta equals U minus V. Everybody's okay with that? Okay. So what I'm going to do now is I'm going to take, imagine this is on the unit circle here. I don't want to try to draw a circle in on this because it's just going to make it messy. But I'm going to label these points here. I'm going to call this point A. What would the coordinate be for this point A if it was on the unit circle? The x-coordinate would be cosine of U, and the y-coordinate would be sine of U. This point here I'm going to call B, and similarly this would be cosine of V, comma sine of V. Everybody agree with that? Okay? So what I'm going to do now, just to kind of make the notation here a little bit easier on us is I'm going to rewrite this angle theta so that it's in the first quadrant. And I'm going to label the points here A prime and B prime. So A prime is just going to be 1, 0, right? Everybody's okay with this idea? And B prime then would be cosine theta, comma, sine theta. Now, why is it okay that I've done this? Have I changed the size of this angle theta at all? No, right? All I've done is I've picked it up and translated it to a new location. I've done some rotation and all that nonsense. But it hasn't changed the size of this angle at all, right? Everybody's agree with that? Okay. So what I'm going to do now is I'm going to consider the segment that goes from A to B and, A prime to B prime. What can I say about the length of those two segments? They have to be equal, right? If that angle theta is the same size in both drawings, the length of that segment from points A to B has to still be the same. Does that make sense to you guys? Okay. So what I'm going to do now is I'm going to actually calculate the length of those two segments using the notation from AB and then using the notation from A prime, B prime. So if I want to calculate the length of this segment, what do I need to use? From geometry? The distance formula. Does anybody remember the distance formula's equation? It's the square root of
x2 minus x1 y2 minus y1.
x2 minus x1 squared plus y2 minus y1 squared. Everybody's okay? Remember that? Okay. So if I go and do this for AB, I'm going to have cosine of B minus cosine of A. That's going to be V, and that's going to be U squared plus sine V minus sine U squared. Everybody's okay there? Okay. If I do it now for A prime, B prime, I'm going to have cosine theta minus 1 squared plus sine theta minus 0 squared. We're good with that. Okay. What I want to do is I want to get, I'm basically trying to solve for, or just simplify this down kind of on each side as much as I can maybe. I'm trying to get a theta, a sine or cosine theta on one side, and then sine of, or cosine of U and V on the other side. Because what we really have here is that theta is the difference U minus V, right? So what I'm going to end up with is a angle difference formula when I'm all said and done. Does that kind of see where we're going now? Okay. So if I have this, what's the first thing I would do to simplify this? Let's get rid of the square roots. How would I do that? Square both sides, right? That'll nuke the square roots. And at the same time, let's FOIL these things out. So this is about to get real ugly. No, I don't. I think that just sit and watch. I think you're good.
The whole time?
Yeah. Well, what I'm doing is I'm deriving some of these identities that we're going to use right now. And you don't need to be able to derive these identities. So that's the left-hand side. And then if I do the other side, everybody okay with what I did there? Okay. All right, let's look at what we have going on here and see what I can simplify. I see a cosine squared v plus sine squared v. That's 1. I see cosine squared u and a sine u, or sine squared u. That's another 1. And then I have the 2 cosine v times cosine u minus 2 sine u sine v. And then down here I see the same thing, right? I have a sine squared plus theta and a cosine squared theta. And then I still have minus 2 cosine theta and then the plus 1. Everybody's okay there? Let's group up the like terms. 1 plus 1 is 2. And then if you look at the left-hand side, I see there's a greatest common factor of 2. Same thing here. If I add the 1 and 1 together, on the right-hand side, there's a greatest common factor of 2 as well. Everybody see that? So let's divide both sides by 2. Get rid of that. Everybody's okay there? Yes? Now if I can subtract 1 from both sides to get rid of the 1s. Everybody agree with that? Yeah. And I can divide both sides by a negative. And I have this, right? And remember now, what is theta equal to? It's u minus v. So what can we do with this formula now? Which is what we have. I can ask you to do something like calculate the exact value of 15 degrees. If I'm asking for an exact value, this is a point where you could start taking notes again. We're done with the derivation. So I would include this box that we made here. That's the identity that we just derived. We're going to use that identity now to answer this question, to calculate the exact value of cosine of 15 degrees. They are V's and then U's. So the U's have tails, the V's do not. Okay? So I'm going to start with cosine of 15 degrees. And I want to rewrite 15 degrees as the difference of two angles on my unit circle. So are there two angles from my unit circle that when I subtract them, I get 15 degrees? Probably. Okay. What are some angles from our unit circle? 0. Okay. What else? 180. Okay. Somebody said, did I hear 45? That's 1. 60. Wait a minute. 60 minus 45 would give us 15, right? Is that the only pair that'll work? Definitely not. Like there's lots and lots and lots of them, right? You could do 45 minus 30. You could do, many, 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 many ones. It'll all be fine, though. Okay. So I'm going to rewrite 15 as 60 minus 45. So in my formula, the 60 is my U and the 45 is my V. So I'm going to have cosine 45 times cosine 60 plus sine of 45 times sine 60. Everybody okay there? Okay. So, yep. Now, if I go to my unit circle, each one of these I can evaluate exactly, right? If I go to my unit circle, what's the cosine of 45? It's the square root of 2 over 2. What's the cosine of 60? That's 1/2. What's the sine of 45? Square root of 2 over 2. And what's the sine of 60? Square root 3 over 2. So if I simplify this down, I have root 2 over 4 plus root 6 over 4. So I would just write this as root 2 plus root 6 all over 4. Not bad, right? That's the answer. That's your exact value. Notice we did that without having to do a calculator. So what this does now, what these formulas are going to allow us to do, is I can now evaluate angles that are not on the unit circle and still get exact values for them, right? I wasn't able to do that prior. I could only get exact values for unit circle angles. I can now get exact values of anything I can write as the difference of two unit circle angles. So what if I wanted to do cosine of 105? Okay, so I'm going to go to my unit circle and find two angles that when I subtract them, I get 105. Are there going to be just one pair of angles like that? No, there's going to be lots of them. You just got to find one pair of angles from our unit circle that when I subtract them, I get 105. Take a look at your unit circle. It's on the back of your identity sheet that you should still have handy, right? And let's find two angles that when we subtract them, we get 105. 150 and 45. Perfect. Okay? So, 150 is my U, and 45 is my V, right? If I'm using my formula up here. So if we just plug them in then, I have cosine of 45 times cosine of 150 plus sine of 45 times sine of 150. So I go to my unit circle and I just read off these values. And I get negative root 6 plus root 2 all over 4. Right? Not too bad, right? What's the hardest part? Probably just finding the two angles that subtract the correct way.
And you can just find that out, just like that into.
Yeah.
Like there's not a specific way, you're just like, oh, choose.
You just got to find two that work. Doesn't matter which two. The signs will all work out so that it'll be the same each time. So if you picked, say, like 315 and 210, that would have worked also. It'll end up like negatives will end up canceling to make the square root of 2 positive and the square root 6 negative. Like they all work out to be the same thing. Okay? So we have differences for cosine. We can also do this for a sum. So how would we prove this? I would do this. Oops. So if I use my previous identity, I can get this for basically nothing. I don't have to go through and do another long derivation here. Remember that cosine of a negative is just cosine of the positive. And sine of the negative is negative of the sine. So the cosine of u plus v is the exact same thing, except we're subtracting instead of adding. So that's our second identity. Usually, we compact these two identities down into one statement. And we write it like this. So notice here we have the plus and minuses. inside this formula. So the way we read this is if I want to use the u plus v, I'm going to use the top sign in the other one. And if I'm going to do u minus v, I'm going to use the bottom sign. So it's both formulas. We've just combined them into one statement because we're mathematicians and we don't like to rewrite things a bunch of times. When we can combine them into one statement, we're going to do that because we're lazy and we don't like to write more than we have to. You guys are burgeoning mathematicians. You're burgeoning mathematicians. Burgeoning. Like you're on the verge of becoming a mathematician. Like you're becoming one. Okay. So, we're also now going to do the same thing for sine and tangent. We could do this in a similar fashion by constructing these. I'm not going to do that, though, in the interest of time. We're just going to give you the formulas. You can use whatever letters you want in yours.
Why are you doing this? Why are you doing this?
I don't know. That's what my notes have. You could use like alpha and beta. You could use X and Y. You could do whatever. Chicken leg and taco. Whatever you want to use as your variables. That doesn't matter to me.
But now I don't know.
I'm in it. Like, yeah. Does it matter?
They're just names for variables. You want to change it?
Yeah.
All you do is say let u equal x and v equals y, and then you can just say tan of x plus or minus y equals tan x plus minus tan y over 1 minus plus tan x times tan y.
1 minus plus. That's the same thing as plus or minus?
Nope. So what we said was with these, what we're doing is we're writing both formulas at the same time here, Bella.
Yeah.
So if I want to use tan of x plus y, I use the sign on top for the sign, or tan of x plus y. If I wanted to do tan of x minus y, I'm going to use the sign on the bottom. So this is just two different formulas we've written as one statement, though. So, for example, if I wanted to do, say, tan of 75, I could write this as tan of 30 plus tan of 45, right?
Yeah.
So, because I'm using the plus formula here, I'm going to use the top sign in my formula. So I'm going to have tan 30 plus tan 45 over 1 minus tan 30 times tan 45. Yes.
No, we have to memorize.
If I didn't make you memorize the other formulas that were way easier, I'm not going to make you memorize these ones.
Hey, I'm not sure.
I don't know, just letting you know. Then your teacher's not a crazy person. All right. Bella, you good with how we're reading that formulas then?
Oh, yeah.
How to use the plus minuses and minus pluses?
Yeah, thanks.
Yep. Okay. All right. Suppose that I gave you this and asked you to rewrite this as a single trig function. Nope. Stop talking, please. Stop talking. Stop talking. So suppose I want to write this as a single trig expression. What I'm going to do is I'm going to look at my identities that I have and see if there's one that looks like this. I'm going to assume that, say, U is 47 and V is 23. So if I look at that, that looks like this one, right? So because we're subtracting here, this is going to equal sine U minus V. So that's going to be the sine of 47 minus 23, or just sine of 24. And we're done. Look at the difference of sine, or the sine of the angle difference formula for sine that we just wrote down. Bella?
Yeah.
So look at the angle difference formula for sine that we just wrote down.
Yeah. Looking at it.
Doesn't this look like the same setup that we have in our problem?
Yeah, it does.
So that's how I knew that it was going to be, because it was the subtraction. I know it's going to be the subtraction here. So U was 47 and V was 23. So it's just going to be sine of 47 minus 23.
And then you do the minus.
Also sine
I'll get it eventually.
plus or minus is
The sign is the same for the sines, yes.
and you do
It's the opposite for cosines.
okay.
Wait, Mr.
And then are they both UV?
Uh,
Or you want the same?
yes, they're both UV.
Because you have the plus or minus, you could just do either one.
No.
I'm confused.
So if this was a plus, that would have been a plus.
Yeah, but it's a minus.
That's
So it's just a minus.
right.
Oh, that's easy.
Yes. Thank you. Alicia! They had some spelling with your name. Yeah. All right. We're going to do one more example and we're done with this first section, okay? All right. So this is like a verifying problem or a proving the identity problem. Stop talking, please. Which side should we work on?
Right side.
Definitely the left side. Why the left side?
Left side. You're just looking at it from a different way. Exactly.
I would because of the 3x here.
I was thinking the same thing.
So Anna's correct in saying we can use the u plus v formula.
All right, Anna.
Oh wow, that's coming along.
So I'm going to think about cosine of 3x as cosine 2x plus plus x. Everybody's okay with that? Now go and look at your cosine angle sum identity. Are we okay there?
Yes.
Okay. So let's look at what we're trying to get to. We have one of them already. So we're not going to touch that one. We're going to work on the other stuff. What do you see that we can do with the other stuff? This sine 2x is what I'm going to worry about changing. So if I go and I use my angle, or I'm going to think about sine 2x as x plus x.
It's been a great class.
And then you guys try to finish this up for next time for me. Okay. We've done the hard part now.